All right, so in this video, we continue in chapter 6. And if you remember from an earlier video, there were 4 ways that we were going to measure how good an estimator was. The first was bias. Well, we're done with bias, and in this video, we're going to cover the second and the fourth. So the second was efficiency and the Kramer-Rao inequality, and the fourth was consistency, which we'll get to. The final video, we'll do the third one, which was mean squared error. Okay, but these two fit nicely on 3 panels. All right, so pause, copy, play. All right, so efficiency and the Kramer-Rao inequality. So let's say you've got a great situation in which you found 2 unbiased estimators of theta, theta 1/2 and theta 2/2, okay? And the question is, well, which one should we prefer to use? Well, if it turns out that the variance of the first estimator is less than the variance of the second estimator, then we say that theta 1 is a more efficient estimator than theta 2, and we prefer theta 1. And that should make sense. Now, with both of these estimators, you expect them to give you the true value of the parameter. But obviously, with random samples, you're not always going to get the expected value. You're going to hopefully get close to it. Well, how close to it you can expect to get is based on the variability. The lower the variability, the closer your outputs hug the mean, right? So if you've got less variance and you're unbiased, you expect to get close to the true parameter. And you expect that if you're off, you're not off by as much as with the other estimator. All right, let's do an example. Let's suppose I have a random sample of 3, x1 through x3. They're independently, identically distributed random variables from some distribution, mean mu, variance sigma squared. And I've got 2 estimators for mu, the mean. My first estimator is the sample mean, x bar. My second estimator I'll call y bar. It's 1/6 of x1 plus 1/3 of x2 plus 1/2 of x3. So this is a weighted average. I mean, maybe it's like exam 1 is a 6th of your grade, exam 2 is a 3rd of your grade, and the final exam is half of your grade. Okay, it's a weighted average. Well, I'm going to show you both are unbiased. We know the expected value of the sample means an unbiased estimator of the mean. Okay, so great, we're done. Let's check the expected value of y bar. And again, in fast motion this time, the expected value can distribute over addition, and the 1/6, the 1/3, and the 1/2 can get dragged out. And the expected value of each of these x's is mu, because they're a random variable from that distribution. So I get a 1/6 of a mu, a 1/3 of a mu, and a 1/2 of a mu. And if you do the common denominator of 12ths, you get 12 over 12 mu. So both of these are unbiased. They both have an expected value equal to the parameter mu. Let's calculate the variance. Well, the variance of x bar. 1/3 can get dragged out of the variance as a 1/9. And then since x1, x2, and x3 are independent, I can distribute the variance across. Each of these variances is sigma squared. So I've got 3 of them. So I've got 3 copies of sigma squared and a 9th out in front. So I have sigma squared over 3. That shouldn't have been a surprise. The variance of the sample mean is sigma squared over n. Okay. All right. Let's calculate the variance of y bar. Same story. Variance can get distributed across the addition because these 3 variables are independent of each other. And then the constants can get dragged out by squaring them. So I get 1/6 squared variance of x1, 1/3 squared variance of x2, and 1/2 squared variance of x3. So all the variances are sigma squared since they're random variables from the distribution. So there's my sigma squared factored out. There's my 1/6 squared, 1/3 squared, 1/4 squared. If I common denominator them, I get 14/36 copies of sigma squared, which turns out to be more than 1/3 of a sigma squared. 1/3 would have been 12/36. So it looks like y bar has more variance than x bar. So I'm going to prefer x bar. It is the more efficient estimator of mu compared to y bar. All right, well, that leads to a good but perhaps not obvious question. So pause, copy, unpause. All right, well, so if we've got unbiased estimators, I want low variance. That's my preference. Well, how low can I possibly expect to get? Because let's say I find an unbiased estimator, I calculate its variance, I'm like, should I keep looking? Is it likely that there's some more unbiased estimators with lower variances that I could use? So this gives us sort of a lower bound on what the variance can possibly be for an unbiased estimator. Okay, so let's let x1 through xm be a random sample from a distribution, and let's assume it's a continuous distribution. It's got a PDF, it's got x, and it's got some parameter theta in it. Okay, that we're probably trying to estimate. And let's assume that this PDF is differentiable. So if I've got an unbiased estimator of theta, then I know it satisfies the following inequality. The variance of my unbiased estimator is greater than or equal to 1 over n times the expected value of the partial derivative with respect to theta of the natural log of the PDF, that partial derivative squared, and then the expected value of it. Okay. That's called the Kramer-Rao inequality. So this quantity on the right, this fraction, that's as low a variance as an unbiased estimator can possibly have. If you find one that's pretty close to that, stop looking. You're about as good as you can get. That expected value is called the Fisher information, I of theta, and it's used in a couple of other settings as well, though not in this class. So that's sort of a throwaway piece of information, okay? And though we say we can efficiency is when we're comparing unbiased estimators. In practice, we often compare the efficiencies of estimators even when we're not sure if they're unbiased or not. Okay, we just like low variance in our estimators. All right, so last panel, going to cover consistency. So pause, copy, play. All right, so this is the fourth way of measuring how good an estimator is. And the idea with consistency is we want to sort of get a measure of, as n gets big, our sample that we're given to, with which to create this estimator, if n gets big, is it good enough, all right? So we're going to let theta hat sub n be an estimator of theta based on a random sample of size n, okay? And we're going to say theta hat sub n is a consistent estimator of theta if, essentially, as n goes to infinity, does theta hat of n equal theta? But in probability, equaling means close, right? So the way we're actually going to calculate it is we're going to take the difference between theta hat sub n and theta, absolute value, and then we're going to ask, what's the probability that this difference is less than a small positive number, epsilon? If, as n goes to infinity, that probability equals 1, no matter how small the epsilon you pick, then we say that theta hat sub n is a consistent estimator, or equivalently, we'd say it converges in probability to theta, okay? Now, this epsilon, being any small number greater than 0, gets us into the realm of analysis, real analysis, which is sort of the theory behind calculus, which hinges entirely upon these ideas of epsilons and deltas, these small quantities approaching 0. So if you think like statistics is what you want to do in life, and maybe you want to go to grad school, I would urge you as an undergrad, take real analysis, which is Math 317, because this is when you learn about these epsilons and the deltas and the limits in really deep detail, which is necessary for graduate work in statistics. And real analysis it's incredibly cool, in my opinion. Okay. All right, so we got this notion of convergence and probability, and it's kind of a tough definition to work with. So it's been proven that there's two conditions that are equivalent to being a consistent estimator. So theta hat sub n is a consistent estimator of theta if two things occur. The limit as n approaches infinity of the expected value of theta hat sub n is equal to theta, and both of these have to occur, and the limit as n approaches infinity of the variance of theta hat sub n is equal to 0. These are a bit more easier to get a grasp on. If you can prove both of these things, then you've got a consistent estimator, okay? And then you just say, well, as long as I got a big N, I'm going to use this estimator because I know it's consistent.